This video is part of the Introduction to Computing Systems Engineering course and covers the lecture material on assemblers. Looking at the course structure, we see that we have finished the design of the hardware platform of the hack computer. We defined the machine language and the assembly language, and now we will design the translator that translates the code from assembly language to machine language. This translator is called as assembler. The video lecture has two parts. In part 1 we introduce what is the role of assemblers, and in part 2 we discuss in detail the hack assembler logic and implementation. So why do we spend time with assemblers? Well, first of all, assemblers are the first step up in the software hierarchy ladder. This is the first time when we translate from one programming language to another programming language, from assembly to machine language. This time this translation will be relatively simple, so this is a good practice before we actually write more complicated compilers. Why to care about compilers in general? As we will see, they reflect very well the challenge of designing programming languages. The program translation challenge in general is the following. We have a source code and then we have a target code. During translation, we should extract the program's semantic from the source program using the syntax rules of the source language. That is, understand what the program is doing. This is the program semantic. The syntax rules are the set of grammar rules that define the language. Okay? Once we did that, we need to re-express the semantics in the target language using the syntax of the target language. If we look at our assembler, what we have to write, we will see that it will be rather simple. Why? Mainly because it translates each assembly instruction into one binary machine instruction. One line code in assembly will become one code, one 16-bit code in machine language. Why we can do it once? Because the instructions were designed this way, because all variables are 16-bit binary numbers, and because there is no complicated program structure. We have one file, we have no modules, functions, subroutines, etc. Also, the translation will be relatively simple because all symbols, variables, labels are global. Okay, so once they are defined, they are used in the entire program. It will mean that the allocation of the memory will be relatively simple. Okay, so to recall a little bit how an assembly program looks like. An assembly program is a stream of text lines, 1, 2, 3, 4. When each of these lines is one of the following, it can be an A instruction, like at I. It can be a C instruction, like m equal to 1. It can be symbol declaration or label declaration, like this declaration of loop. It can be comment, like this program computes blah blah blah, or it can be white space that we actually do not have in this example. Okay, so we would like to translate this code into a sequence of 16-bit instructions. How will we do that? Let's say one by one. If we have an A instruction, and it looks like at and some value. If this value is a decimal number, then we simply translate this code by inserting the binary version of the number. If the value is a symbol, then we have to find the right number for this symbol, right? Then actually the right memory address. Then we need symbol handling, and this we will discuss later. C instructions. As you remember, the C instructions has this structure. It starts with 3 ones. Then we have a couple of bits defining what the computation will be, then a couple of bits defining what the destination will be, and a couple of bits defining the jump condition. The symbolic representation of a C instruction, that is the assembly instruction, has the form of a destination is equal to the result of a computation, and then we might have a jump condition. From this instruction, the destination field and the jump field may be empty. The translation of the separate fields are simple because we have these nice translation tables for computation, for destination, and for jump conditions. This ends the part on the introduction of assemblers.